To summarize our results, we find that the delivered voltage of the test e-cigarette was quite different than its labeled voltage, but it did vary quite linearly, as we can see, with a correlation coefficient of 0.9999. But it wasn't very indicative of the settings that were on the dial. We also see that there's a linear relationship between the mass loss per puff and the power delivered to the atomizer, with an 86-fold increase as we go from 2.9 watts and 3 watts to 11.9 watts. Our size distribution data shows that there's a smaller abundance of nano-sized aerosols as we increase our e-cigarette power. This trend is seen not only with the e-cigarette battery, the real e-cigarette, but also when we hot-wired an e-cigarette battery and drove it with a laboratory power supply. We can see that as voltage increases, or power to the device increases, we have a reduction in our population, or our count concentration, of nano-sized aerosols. Secondly, we also see an increase in particle count around 1 micron as we increase the power to the e-cigarette, or to the atomizer of the e-cigarette. This is also seen in the e-cigarette test device and our hot-wired battery driven by the laboratory power supply. As voltage is increased, meaning power is increased, we see a definite increase in this previously unreported peak at roughly 1 micron. For our mass distribution data, we can see that the results may be slightly deceptive if you only look at size distributions. Size distributions indicate there's less nano-sized aerosols, which would make us think that there's less e-cigarette aerosol being formed at lower power. However, considering that the mass of an aerosol is a function of its volume and density, and as we increase from 100 to 1000 nanometers, that tenfold increase is an increase of 1000-fold for a spherical particle. The mass of the particles that are at this previously unreported peak, roughly 1 micron, is far outpacing the mass that was lost by having a lower population or a lower count concentration in the nano-sized region. We also puffed a regular tobacco cigarette just for comparison purposes, and you can see that our median size distribution, our median size is roughly 300 nanometers and 800 nanometers. And we can see that we have more mass due to those larger particles in the 300 nanometer range in the cigarette than we do in the e-cigarette nano-sized aerosols, and somewhere in between the low power and high power. These trends of an emerging high mass peak at around 1 micron are quite evident as we look at our hot-wired laboratory power supply driven e-cigarette test device. As voltage is increased, or power is increased, we see a definite increasing in the mass that is found here at 1 micron. We also should note that there's quite a bit of mass found in the very few particles that are around 10 microns and larger. This is not of great impact because these particles get trapped in the upper respiratory tract. As we look at our cumulative mass distribution, what we see is at the mass median diameter, or at the 50th percentile of accumulated mass, we have quite a smaller median mass at high-powered e-cigarette setting. We have 1.6 micron diameter of average mass, whereas we have roughly 10 micron for cigarette smoke and for low-power e-cigarette vapor. This is also clearly observed in our multi-power settings generated by the laboratory power supply.